Hello everyone, Mrs. Patel Dame here for topic 9.5, free energy and equilibrium. So essentially, we're trying to figure out if a reaction will occur, proceed in the forward direction, if it's at equilibrium, and that if it's going to proceed in the forward direction, that's telling us about delta G. So essentially, a system at equilibrium, that's dealing with K, whether or not it's going to be thermodynamically favorable, that's dealing with delta G. So some equations for this. We know, looking at our AP reference table, first of all, the last one that we had, delta G, over here is going to be delta G. We had products minus reactants. That was in the last topic. Also in the last topic was delta G is equal to delta H minus T delta S. So both of those are in there. We also have delta G is equal to negative RT ln K. So this is when we are dealing with the equilibrium constant, or K. So this is the equation that we have for this one. We have delta G, standard conditions, are equal to negative RT times ln, and ln is your natural log of K. If we have to flip it, for instance, if we are solving for K, we're thinking about K is equal to, well, look at your natural log button down here. Its little other symbol, like right above it, is going to be e to the something power, right? So that's essentially what we are doing. Your K is equal to e to some power. So essentially what you're doing is to get K by itself first, you had to divide both sides by negative RT. So that's what this is being raised to. So it's e to the delta G to the negative RT. But that negative can just be anywhere in there. So if you need to go from this equation and then solve for K instead of solving for delta G, go back to your calculator, find natural log. You know that the opposite of natural log is e to something. And then you're dividing both sides by negative RT to get that by itself. All right, so taking a look at number one. Let's go back to R. R we know as being one of the constants. So it was our gas constant when we dealt with we used 0.08206 liters times ATMs over mole times Kelvin. And then we had torr instead of ATM. So that was a 62.36. So these two equations we used for gases. This one right here is what we are using now for this R. And we know that because this time we're dealing with energy, not with pressure and volume. So this value for R is going to be 8.314 joules, and that's over essentially 1 mole times 1 Kelvin. Knowing that this is part of this, I'm looking at that temperature, that K, and that's in Kelvin. All of these problems should go into Kelvin. So for example, this 25 degrees Celsius, we need to convert that to Kelvin. So we add 273 to it to give us 298 Kelvin. So even before I begin that problem, I've got that part of that in there. So we're dealing with calculating delta G at 298 Kelvin when carbon monoxide gas is at 5.0 ATM and hydrogen gas is at 3.0 ATM. So I've got carbon monoxide plus H2 gas is in equilibrium with methanol, so CH3OH. I know this pressure was 5.0 ATM, and this pressure is 3.0 ATM. This is in equilibrium, so I can get us our equilibrium constant, essentially. So I know that I can, from here, determine what my K is. My K is my products over reactants, eliminating any solids or liquids. So essentially, my K is equal to 1 over the pressure of carbon monoxide times the pressure of H2 gas, but that is raised to the second power. So it's still products over reactants. We just don't have anything in the product because it's a liquid. So we're just going to put 1 in there. I'm using the P because these are in pressure. If it was in concentration or molarity, I would use the brackets. And then I've raised this to the 2 power because I have the coefficient of 2 right here. So I can use this to help me figure out what that K value is. So I have 1 over the pressure of carbon monoxide, which is 5.0, times the pressure of hydrogen, which is 3.0, but I have to square that. So essentially I have 1 over 5 times 9, so 1 over 45, so my calculator going, 1 over 45 is equal to 0.022, and that's the 2 sig figs. Recall that K does not have any units. Don't forget, you want to put your K expression in there first because you never know when you're going to get a point for that. So now I can solve for delta G. And I can use this equation as is. So delta G is equal to negative RT ln K. So the R is 8.314 joules over 1 mole times 1 Kelvin times my temperature, which is my 298 Kelvin, times the natural log of K, so the natural log of 0.022. I can cancel out K. I'm then left with joules over moles, and I think I'm good to go with those units. So let me throw this into my calculator. Got negative 8.314 times 298 times natural log of 0.022, and I get a big number. Well, that makes sense. This is in joules. So let's see, I don't know if you can see my calculator. My apologies if it's too much in the shadow. So that's 9,456 joules per mole. If I wanted to put this into kilojoules, which it's not asking me to, so I don't have to necessarily, but just to remind you, this is my decimal point. You would divide by 1,000, so I go over 1, 2, 3. So that's equivalent to 9.456 kilojoules per mole for my delta G. So thinking about this reaction, it's positive, right? So if it's positive, it's probably likely not thermodynamically favorable. So delta G is positive, or delta G is greater than 0. My K, looking at my K, it's really teeny tiny, right? So in this case, my reactants were much larger than my products. So my K is less than 1. And looking at those two conditions and my values, I can say that the reactants were favored. So my reactants were favored because delta G is positive and K is less than 1. So the reaction proceeds in the reverse direction. Sorry about saying that they were favored, but the reactions are proceeding in the reverse direction. And I'll throw that in there just because of that. Because delta G is positive and K is less than 1. Cool. So now we're going to calculate for K. Well, we know that K is equal to E to the negative delta G over RT. I can say I have E, and then my delta G is 22.7 kilojoules per mole. I know my R is in joules, so I've got to convert one from one to the other. So I'll just do this one. So this one is in kilojoules. I'm going to move it over. I'm going to essentially multiply it by 1,000 to get me to joules. So 1, 2, 3. I have 22700, and that's going to be negative because I'm going to maintain my negative value there. And that's joules over mole. Then I'll put in my RT. My R is 8.314 joules over mole Kelvin, but because it's already in the denominator, I'm going to put that mole and that Kelvin at the top. And I have 150 degrees Celsius, which is equivalent to 423 Kelvin. So looking at my units, I can cancel out Kelvin, I can cancel out moles, and I can cancel out joules, which is great because K is a unitless number. So to put this into my calculator, I have second ln, so I got my E, to the negative 22700 divided by, and then I have a product down here, so I want to make sure I make this a product. Sorry, that might be better. Divided by, and then in parentheses, 8.314 times 423. Make sure my parentheses are all set. And let's see, what did I mess up there? Oh, because I did a minus sign instead of a negative. Silly me. All right, cool. So that K value is 0.00157, I want to say, for sig figs. Remember, this is a unitless number. Your K is really, 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 really small. So the reaction will proceed in the reverse direction. And then we can also say that because delta G is positive and K is less than 1. And this is also really what we're looking for. Cool. So the following table here, we have 3 conditions of K. When K is greater than 1, when K is less than 1, and when K is equal to 1. I also have these values here for delta G. So when delta G is less than 0, meaning when it's negative, when it's greater than 0, when it's positive, or when it's just 0. So if K is greater than 1 and delta G is negative, that means that we are going to favor the forward direction, meaning we will make more product. When K is less than 1 and delta G is positive, that means that we're going to favor the reverse direction. We'll make more reactants. And when K is equal to 1 and delta G is equal to 0, that means that we are at equilibrium. All right, let me know if you have any questions. Take care.